There we go. Second chance. There
Okay.
you go. So we took a second take for Michael to get his hair in order. But welcome back. We are here on week two. Guess I can go to my super amazing slide deck. Let's do that. So we're on week two. Welcome back. Thank you for coming. This is the boot camp. We're talking about algorithms, data structures this week. Last time we wrapped up walking through some algorithm practice, and I sent you all a set of practice problems to work on. And when I walked through, I showed you the example that I did, and I showed you some somewhat better solutions, more efficient looking solutions. Today, what we're really going to talk about is how you judge what's efficient and evaluating the algorithms and the data structures, kind of deciding which ones you're going to use and what's best fit to the purpose that you're trying to solve. It's a really deep topic, so we're not going to obviously be able to cover all of it in just this time. This is also the most computer sciencey thing that we're going to do in this course. So this is the place where there could potentially be a lot of math. We're not going to get into the math, but it's there. So if you go and look at these on your own, this is the place where you're going to run into, linear algebra and all these other more complicated things. Don't sweat it. You don't need to do all these things right now. It's good to know they're out there. It's good to understand the choices you're making when you're choosing things, but you don't need to get really deep into it. Really, the way I like to think about it is, what we've done up to now is I've kind of given you or not given, but I've shown you where the tools are to grab materials, and I've shown you how to make a workplace and build things, put things together. So if you think of the analogy of, an automobile, a car, like we were using with the classes in the last example or last class example, um, you could do that same sort of thing. We've built a small sort of motor with our applications, and we have all the places that we can build more complicated things. But these algorithms, data structures we're going to talk about here are sort of the more deep level engineering that is required to do really big scale operations. And we'll get into all those sorts of things about how we choose what we're choosing when we're making our algorithms and choosing our data structures. But before we dive into today's content, I want to talk about that problem set. Did anybody get a chance to do any work on it in the last couple of days?
I was still working on the last lesson. Didn't get to it.
Didn't get to it. Anybody else? Anybody take a swing at any of those?
When you say
Yeah.
couple days, you mean the one day between meeting?
Yeah. Yeah, the one day since last time we saw
Yeah,
you.
I didn't get a chance. That my life just goes too fast.
Okay. Okay. So nobody's looked at the problem set, which is fine. That's all
I've
right.
got
That's
about a
okay.
third of it done.
You got a third of it done?
Yeah.
Nice.
Okay. Cool. Cool. Are you stuck anywhere, or is that just how much time you had for them? Are you finding them fairly simple?
Uh, well, I got a little hung up on the counting sheep one for some stupid reason. I could get it
Oh,
to
really?
work perfectly on my computer, but pasting it into the web page, they were unhappy about some way I was handling it, and it took me a while to work out
Huh.
that the print statement as of Python 3, you can do a comma and say an end, right? But
Mm,
normally it defaults by putting an end of a line return. But you could
okay.
change that end. So I was using that end statement to add the three dots rather than a line return because I didn't want it swapping lines. I wanted to keep continuously paste this onto the same line. Well, they had a different idea of how that code should be working.
Mm.
And even though the output matched what they said, it failed all the tests because their test was looking for specific string matches
Would
that
Would
weren't
you be able to show it?
occurring.
Would you be willing to share and show us?
I'm sure. Let me see where I've got that.
Because I would love to walk through what you're seeing and kind of use it as an example for other folks if they're working on the same problem. And again, if you
Right.
haven't got to the
Should I
problems,
just, I could just paste it into the chat here.
well, here, no, I'd love it if you would just if you try. Can you
And
recreate the problem, or did you solve it?
I did get it solved and moved
Okay.
on.
Okay. Well, then never mind. That's fine. Are you stuck anywhere else, or are you just that's how many you got through?
Now, once I got past that, then I did the cards and then the um, case matching the letters.
Uh huh.
I was a little more verbose in my code than what the some of the nicer solutions were,
Yeah, that
but
happens.
I like to see what I'm doing, and a lot of people are very good with their just implied progress of the code.
Okay.
I want to know that there's specific things that I'm setting, that this is going to be a variable that I'm setting to true because of a certain condition. And
I
they'll
get
take
you.
that whole condition and drop it into the formula. I just got crank it all out in one step.
Okay.
And that's nicer to look at, but not nicer to read.
Right. And that's a good point.
You know.
When you're doing all these, there's that kind of balance between the efficiency for the machine to read it and the efficiency for a human to read it. And when
Right,
you-
because I'm figuring when I'm going south on this and I'm getting something wrong and I don't understand why, when I'm breaking it apart into smaller chunks and taking a look at what each chunk is intentionally doing,
Mhm.
I have a better chance of getting it worked
Exactly.
out.
Exactly. And that's also something to keep in mind when you approach other people's code in bigger projects. Like when you're doing these problem sets, all the code
Yeah.
you're writing is in isolation and not in bigger context. And you're not going to really be sharing it with anybody to work collaboratively on it most times. There you can in code wars compete with each other and do like refactoring back and forth of problems and see who like does the most efficient code, right? So that's one of the training tools that they've got built into it. But yeah, when you're actually writing stuff, that's one of those things you got to keep in mind is other people are going to have to read it. So,
Yeah.
to limit
Well,
the
even you
comments.
will.
Right. And
7 months from now, when you're trying to go, oh, geez, why is this working out bad?
Yep.
Oh, well, way back then I was doing this, and
Mhm.
now you've got to go back and kind of untwist what it is you were doing at the time to fix the downstream data that you're dealing with.
Exactly. Exactly. All right. So you're rocking through those. That's good to hear, Chris. Are they challenging at all? Are they fairly straightforward solving them, or have you had issues
Yeah, I
with them
think
generally?
I think the biggest issue I've got with them so far is just I'm very used to Ruby and how I should be doing this, so that when I'm doing a count, it would be whatever the variable is dot times, and
Oh, I
Ruby
get
will
you.
just just iterate through it that many times, whatever that value is.
Okay.
Whereas with just figuring out just the different syntax usages, it's
I get you. So you understand
No.
that you've already got a handle on the basics of doing these things. You're just doing it differently in Python.
the thinking, yes. And
Yeah,
now
I
I've
get
just
you.
got to learn and kind of just that, like you said, the muscle memory. You got to
Mhm.
do it and do it and do it and do it. And eventually I start getting these commands like, dot is lower.
Right.
Okay, that's a
Yeah.
string value. That's a function
Yeah.
within the
Yeah.
string object. I can
Yep.
just is lower, is
Yep.
upper.
Yep.
I can leverage those. Whereas if you don't know they exist, it's kind of hard to know to use them.
Right. Right. Right.
So
That's it. Yeah. That's
a
a
lot
great
of it
point.
is
Yeah.
looking up the manual and going to a site and looking up, okay, this is Python. What does the string object have?
Yes.
And that is just a slowdown. It takes you time. And
Yeah.
eventually you start getting those things in your head. These are the common ones, the
Mhm.
ones that you utilize a lot.
Yep. And that's really the point of this practice. And that's a great call that all the things that we've used. So like when you make a string, it's really just an instance of a string class, and that has a bunch of methods that are built into it. So we did the split method last time when we were solving the URL problem, and that's just built into the string class. And there are plenty of other ones. So go into the documentation and reading about the class and the methods that come with it is really helpful, because then you can find all these super cool things that you can do that make it shorter and faster to solve these problems or get done whatever you
Yeah.
need to. Has anybody else had a chance to go through problems at all besides Chris? I know we had some people joining while we were talking about it. If not, I will shame you heavily. No, but you should really do this as much as you can and find time to practice. And don't feel bad if it takes a while to get through them. The goal for moving up in levels and getting more complicated on things is if you're knocking these out in, less than even the complicated ones, less than 45 minutes at the most that you're spending on these. So if you're really stuck on one, you can't figure it out, it's taking you longer than that, don't worry about it. That's okay. It just means you got to practice more, and that's not the end of the world. So definitely work on those. There's not going to be any more specific ones we're going to add to it. That's going to be the list. I really encourage you over the weekend before our next session, work on them. We can talk about it. I've got solutions to them that I've worked through. So if you get really stuck, we can figure it out. And if you knock these out all the way, like, Chris, you're saying you're most of the way done with it, then there are endless amounts on there of higher levels in those things that I sent you over. So
Yeah, it's
lots
not
of
bad.
practice on that. Yeah. Cool. All right. So if nothing else about that, we could just go straight into today's topic, which is talking about algorithms at a slightly deeper level and how we evaluate and choose which algorithms we're going to use. And before we go straight into some of that, I want to talk about this topic of recursion. It's an idea that's really cool, but somewhat slippery to understand. And I want to make sure everyone's really clear on it. So it comes up in a lot of different places. And one of the ways that's easy to see, I'm actually going to do this, where I'm going to do a demonstration of recursion. Hopefully I don't crash my computer doing this. But the idea of the recursion is things that are just self-referential. So something that refers back to itself. And if you've ever stood in between two mirrors and seen your reflection over and over again, that's recursion. And I'm going to try, I was trying to find like a picture to try to hammer it home for y'all, but I figured doing it here in another video chat and sharing my screen will affect that. Like Zoom didn't, it's apparently Zoom has solved this problem, but Google Meet still does it. So I'm going to open this meeting and I'm going to try to demonstrate recursion for you by sharing my entire screen. And what it's going to do, if you've ever done this by mistake, is it should show my whole screen over and over again in a bunch of progressively smaller boxes. And it should give me this little warning that says, hey, if you don't want to do this infinity mirror, you know, don't share the screen you're on. But I do want to do the infinity mirror. I want to show you that. So you look at this and you see that it's my entire screen over and over again inside of itself, infinitely down till you can't see it. That is recursion. So this right here, it's like an optic recursion. So we're looking at my whole screen, inside of my whole screen, inside of my whole screen, over and over again. So this is recursion in one way that we see it. So I'm gonna turn this off before I actually
Where you
crash
tear
my
a hole in
computer.
space-time. Yeah.
Yeah, or eat up all my bandwidth. I got too many tabs open as it goes anyway. So recursion is a super useful thing to understand in computer science as well, but we also use it in language every day. We use it in most human languages. There are like a handful of Aboriginal languages that don't use it, but most human languages use it all the time. It's kind of one of the things that sets us apart from animal languages like birds, you know, tweeting and making songs. They don't use recursion. And in language, it means that we can endlessly put structures inside of themselves and make bigger structures. So sentences, we can sentences don't have any end. Yeah, go ahead.
Yeah. When birds basically repeat the same song over and over again, right?
Right. And they don't take a song and put it like within another song and make it more complicated. So like what we do in our language, human language for recursion is we can make a sentence as long as we want by just adding I think that at the end of it, and you can add another sentence to it, or you know, he said that, and it just keeps going. You know, like I think that I went to the mall and he said that I saw him there. And you just keep going and going and going, putting more sentences inside of sentences inside of sentences.
Okay.
So that's something we all do it naturally. In computer science, in the way that we do it here in recursion in computers, is when a function refers back to itself and it calls itself. So self-referential functions are the way we get recursion done. I'm going to demonstrate it a little bit. So I'm going to go back to Python Anywhere, and we're going to go into a quick console. I'll do it in the main file. So if you want to do it along with me, you can. But this is something that we can accomplish in other ways. So it's not something you're necessarily going to need right out the gate, but I do really want you to understand how it works, because a lot of the algorithms that we're going to talk about do things recursively. And so if you understand the term and what it means, then it'll just be one less thing to think about when we're trying to learn the other concepts. But it's also really cool. So there may be times that you want to use recursion, things like game loops and stuff like that. When you're making games, recursive function calls are helpful for that. And so there are reasons that you would want to do it, but you can avoid doing this if it's something that you don't want to do. And you can accomplish similar things with the while loop that we talked about before. So I'm gonna give an example of recursion using, unfortunately, some math, but it's not real complex math. So we're just gonna do a factorial. So if you don't remember what that is or know what that is, it's written like this. So this 4 factorial is a 4 exclamation point. And it means that we take all the numbers from that number 4 in our example and multiply it by each number beneath it. So 4 times 3 times 2 times 1, which is 24, is what this 4 factorial would be. So we're going to write a function that's going to do that recursively. And the idea is it's going to take one number that we give it, and it'll recursively multiply it by each number that's below it and give us the sum at the end. So this is We're just going to call it factorial, so we know what it's doing. And we're going to give it a number n. And whenever we do a recursive function, we want to start with what's called the base case. And this is sort of like the while loop that we did, the condition to break out of it. That's what this is. This is what we start with as the bottom of our recursive function. So it's called the base case. So we're going to say if n is equal to 1, which should be the last number that we want to multiply by, or if it's equal to 0, because if somebody inputs a 0, it'll break everything because anything multiplied by 0 is 0. So we don't want to get to go all the way to 0. We want it to stop at 1 when it's going down from a number. But if somebody inputs 0, we don't want it to break. We want this function to return 1. Right? So right now, if we ran it, it would work. It's a fully functioning thing, but it's not going to give us the factorial. It's just going to give us a 1 if one of those things are in there. If it's some other number, it's not really going to do anything. It's just going to look at us. So the recursive part, and this is where it gets cool. It's not a lot of code. It's very simple, but what it does is pretty cool. So the recursive part is the else statement. So the other condition outside of our base case is if it's any other number besides 1 or 0 that we input to this function, we're going to return the number that we got, so the 4 in our example above, multiplied by, and then we're just going to call this function again with the number that we gave it minus 1 to represent the next down number, right? So what's going to happen here is it's going to, when it runs through this code, when we call it and we give it a number, say we give this 4, it won't meet this first condition, so enter this else condition and say, all right, so I'm going to take 4 on the first run is n. So n times this function call with n minus 3, which would be, or n minus 1, which is 4 minus 1 is 3. So the second time it runs through, the first time it basically waits for the second time to run through. And it'll say the second time it runs through where n is 3. And it does the same steps where n is 3. Then it does 3 minus 1 is 2. And it runs again until it gets to 1 and says, okay, cool, now I'm going to give you 1. And so then it returns basically back up through all those calls until it gets to 4 and gives us our final answer. So recursion is not fast. It's very slow. It'll limit what you're doing in some ways, but it's a cool way to get some things done. So I'm going to do a quick demonstration of what I'm talking about by limits and slowness. And this is going to lead us into our efficiency talk and complexity. So I'm going to call it down here a couple of times using the same print idiom that we were doing before. And I'm going to test it out, show 0 with what we had. I'm just going to copy and paste this since I am repeating myself, despite that principle I tried to tell you about. And put in some other inputs. So I'm going to put in 1 just to test our first base case that should just return 1 on both of those. And then we'll do 4 since we know that's 24. And then we'll just do some other number that's larger. So let's just do 10. See how that goes. So I'm going to save it. And I'm going to run it. And this should print out the results of our recursive function. And there we have it. So we got 1 the first 2 times, which are what we expected. That's our base case being run both 1 and 0, spitting out our 1s. And then 24 for 4. And then this beast for 10 as a factorial. Now you got to be careful with this because it does do, it can lead to loops like while loop that will run into limits. And I'll show you if we give a really big number in here instead of a 10, that'll probably bottom us out. It'll give us an error. It says it can't do that. So we get a recursion error. And this says the maximum recursion depth exceeded in comparison. That just means that this operation basically just took too long and it did too many times down and broke the computer and said, stop doing that. And so the interpreter stopped us at that.
So if you had a more massive computer, then that would work, right?
Yeah, that's a good call. So it really is dependent on the compute power, and the input size that you put into it is going to affect how much power you need to be able to process the algorithm that you wrote. So this algorithm is not the most efficient, and it's limited in size. Once we get to a certain size, it's going to break our computing power. Does that concept kind of make sense so far about recursion generally?
Yeah.
Any questions about this? All right.
Okay. Is there a let's say you're doing a factorial.
Mhm.
No, there would be no way, if you were doing a factorial, there would be no reason that you'd have some kind of a test in there to make it stop before it got to the end? Or would there?
Oh, like you mean to test the limits to make sure it doesn't go over the size that you have?
Yeah,
Something like that. Yeah, yeah, I'm sure. Yeah, you absolutely could. You could figure out what your limits are and put in some parameters to slow it down if you really wanted to optimize this so it wouldn't break. Given certain inputs, you could for sure. The way I'd probably do it is probably limit it at the input phase. If you know that it can't handle over like I don't know 10,000 or whatever it can handle, then have people input things and put another piece of logic separately that says, okay, that input's invalid because it's bigger than the number I know I can handle for this other function, and then just leave this function how it is. So you kind of that's kind of like call it separation of concerns, right? So you have two different pieces of code that handle one piece of that issue. Does that make sense?
but it
Cool.
would still stop running it when you get to the limit, right?
Yes. If you well, yeah, if you went past the limit, it would still throw the error. Yeah.
Yeah, okay.
But you could come in with a like an exit or break or something like break condition. If you say that you could just do another like elif condition and say, elif n is greater than 10,000. And this is also something you could do in Python. You can't put a comma to separate numbers, but if you do a number that you want to use a comma in normally, you can do an underscore and it breaks up the zeros instead of just writing all your zeros together like this. So you can just do a condition like this, like it does something else, then you can just use the word break and it just stops the function. It won't break the computer. It'll just exit the code. So, that's an option. We could do that to cap it out if you wanted to. But that's, a better way to optimize is kind of what we're going to talk about here is maybe just picking a different way to approach the problem. Instead of trying to optimize a particular function in your code, maybe doing it recursively is not the way to do it. Or, maybe using the data type that you're using is the right data type to use or something like that. So the way we would evaluate, well, actually, before we move on, are there any other questions? That's a good question. Are there any other questions though, before we break from this? Any other questions about recursion or
Can you think of an example of a good time to use recursion? You gave some examples of where they're used, but I'm missing the piece and what they're used in.
like what you would use them for? Yeah, totally. So we're gonna talk about some of the algorithms that we talk about specifically using recursion in what they do. So like an approach to solving a problem, we'll use recursion to solve a particular problem. And I'll have some specific examples, but generally you'll see it in things like games where a game will run in sort of a recursive function loop and it'll check some conditions along the way to say if a number of points have been met or somebody's lives have been used or something like that. And then it'll call back to itself to keep running within that game and have breakpoints in it. So that's one way I've seen recursion used. But again, we can accomplish these same things with the conditional logic and while loops that we were talking about before. So it's not necessary, but there are places you can use it, and there are. It's more really understanding that this concept exists and like what it is, because when we talk about certain sorting algorithms, for example, that we're going to talk about, they use recursion. They'll recursively go back through until they hit a limit of some kind. So I want to make sure that we understand what recursion is.
Okay.
Does that answer your question?
Yes.
Okay. Cool. Anything else? And we did actually do recursion like day one when we were doing Linux commands and we were removing directories. If you remember, we used the rm command, which normally deletes files. But if you use the R flag, that stands for recursive, and it'll go back through each folder or directory until all the folders are gone, and it'll get rid of files too.
Right.
So that's one use of recursion. All right, cool. So if nothing else, then we'll go on to how we decide and the way we measure an algorithm. Now, this is definitely math, but I'm not going to hit you over the head with this math. And let's get away from these commercials. We don't need to be advertising things. This is a great cheat sheet. I have this in our resources. It's down, I think, towards the bottom. If you go to the resources.
Hey, Jeff. before you
yeah.
move on,
Sure.
So I just had this thought. There was a time when, in File Explorer, how you have nested folders and nested folders and nested folders.
Yeah.
And we wanted to take everything and move it on into a SharePoint list.
Mhm.
But if you're familiar with Microsoft and the SharePoint, it can't. What it does is it takes that final folder, and it's not just SharePoint. This is how it's written, right? It goes like this folder is in this folder, which is in this folder, which is in this folder, and it repeats everything, right? So
Right.
when we were getting into the SharePoint site, trying to like just copy those over, it wouldn't because the string was too long. So this just made me think, could we have used recursion to then extract all of that stuff and drop it into like a single folder and eliminate all of those
Totally.
Are you freaking
Yeah,
kidding
that's
me?
absolutely so those are the kind of uses that you can absolutely do recursive functions for. It does really, really well at, going to the bottom of some kind of file structure and doing something over and over again each time, like gathering up all the files and moving them somewhere or something like that. So
So
yeah.
if at the end of like, say they're nested folders, it won't have all of that string of file naming ahead of the file name. It'll just have that file name, or how does it?
Well, that would be a little specific. And so that's the thing, is that you'd have to, it depends on how you write it and what you're passing from one thing to the next. So if like the limited file name is the problem, then you probably just want to adjust the string of the file name as you're moving things along and make it shorter or something like that.
Uh-huh.
But yeah, that's definitely one use when you have multiple layers of something and you want to do roughly the same thing through each layer of it, like a file structure. If you want to move everything up out of something, that's a really good use of recursion.
Okay. And would that work for every file that has a unique name inside that final folder? Like if there's a folder,
Yeah.
there's 50 folders in that folder.
Mhm.
Those 50 folders have 50 folders. One of those 50 folders has, you know what I mean? And
Yeah,
by
and
the
there's-
time
and-
yeah.
Absolutely. And what you're talking about is really the kind of thing that algorithms can become, is figuring out how to do exactly that. Say, okay, cool. So I know that I can make a recursive function that will like figure out how deep it is until there's no folders left, and then
Okay.
go back up to the next directory and then go back down to the next one and dig
Wow.
into it from there. So you can absolutely code the thing to do that and figure out where it is depth wise. And there are a lot of different structures that you may want to pull the data out and move it into. And that's sort of what we're going to get to today, with like picking a data structure to do exactly that sort of thing.
Okay.
And depending on what it is you're trying to do, you may want to structure the data that we've talked about so far. Because so far we've talked about data types, not data structures.
Mm-hmm.
And so the classes that we did last time, arguably you may think of them as a data structure because we did build them out of other things, other data types that we talked about, but it's still considered a data type in Python. So data structures are going to be the things we talk about next. And it's more like what you're saying, where you have, the data that you have is related to each other in a folder structure now, and you need to move that out and change the structures in and put it in another place.
Right.
Maybe adjust the file names, and it's absolutely what recursion would be useful
Oh
for.
my God. I
So-
can't believe that. We needed,
So yeah,
we
again,
needed a
but
code writer.
but you're
Okay.
gonna get into some of the things that we're talking about now. So this resource that I wanted to highlight on here is one of the tools that you kind of use to choose what you're going to do. So like to your question, Marty, it's a great question, a real specific one. I love that. If anybody else thinks of things along the way that you're like, hey, could I use it for this? Let's talk about it. Because the specific answer to your question, like I really want to hammer home that there is no like best algorithm or perfect data structure or any of those things. It's all dependent on the problem you're trying to solve, the system you're in, the context in which you're doing the thing. So I linked in some good reading in here for all kinds of stuff. There's some Python things. I've mentioned automate the boring stuff before, but another one that's really helpful just conceptually, and it's a really fast read. You can read it as like a manual in about an hour if you just read the highlighted parts, sort of the abridged table of contents, or the detailed table of contents, I think is what they call it. It's called The Timeless Way of Building, and it was this architect in I think the 60s or something that wrote this for architecting buildings and towns, but it become this like cult classic for designing software. And I'll refer to it a lot, especially more when we get in the next couple of weeks when we start designing the web application. But one of the concepts in there that I think is relevant to what we're talking about here is that he talks about how a good configuration will allow conflicting forces in a certain context to resolve themselves. So that's what we're looking for when we're picking making algorithmic choices and making data structure choices, is what's the context in which we're making this decision? What forces are in conflict that we're trying to resolve? So for you, Marnie, when you're talking about the specific case, the context is like the file structure you already have and the system you're already using. The conflicts you have are, the string limiting file names or whatever it is you have that are constraints. And so then you've got to pick the best approach to solve the problem that you want to out of the choices that you have. So, so that's really what you're doing all the time with this. And one of the tools that we use for that is called Big O notation. If you haven't heard this term before, it's straight up math, is algebra. The Big O stands for this German mathematician named it Ordnung or something like that, which means like orders of magnitude. And I linked this I'm about to show you. I linked this down in the resources so you can look this up later on your own. This is great. So we put this together. It's a cheat sheet for this thing. So anybody that's not trying to become a developer, it's not very important that you know how to calculate this and do this. Anybody that is trying to become a professional developer, like this is where you got to be, and you got to know this stuff inside and out. This is the most computer science we're doing in the course, and we won't dive super deep. This is for everybody else who doesn't want to be on a full-on developer like myself. I'm probably never going to sit at Google and be a developer. This is still good to know, because what we're looking at here is a representation of how you can algorithmically look at the complexity of algebraically look at the complexity of an algorithm. So this is looking at the results of algorithms and how long it takes. Over here on the left side, on the y-axis, the number of operations. And the bottom, the x-axis, is elements. So it's the number of operations that you put into it, or the number of elements that you put into it as inputs. And so what's showing here is that as the number of inputs goes up to the right, the number of operations that the computer does, the time it takes to do them, is going to go up too. So all these lines in here, in these different colored areas, are representing different kinds of algorithms and how long they might take. So as you can see, they've color coded this to say the horrible ones are all the red areas. So all this really, really slow stuff. And we've got the factorial we just talked about. That's really slow. And we saw that we broke our instance trying to recursively do a factorial. So any function that you do that operates that quickly, as you can see, you're going to really fast run into a point where you have too many inputs and it's going to go way slow. So that's inefficient. We don't like that. The complexity is really high. And then you have another couple of sets of these. We're not going to worry about specifically what these are called and what they're doing. These are exponential and polynomial time is what they're called. But all three of those are terrible. We want to avoid those for the most part. But sometimes you can't. Sometimes you have to do something that's going to take that slow, and you have to figure out what to do about it otherwise. We're shooting down for these green bottom ones, this O log n as it's pronounced, or O to the 1. And those are constant time and logarithmic time. And so that basically means stuff that doesn't really cost anything. So assigning a variable, for example, is a constant time operation. It doesn't really cost much. And it doesn't matter how many inputs you put into it. It's always going to be the same amount of time. And then linear time is also not too bad. So that's this O to the n up here. And that's where the time goes up on the number of inputs that go in, but it stays in a linear relationship. It doesn't go up exponentially or any of these other functions that go up much faster given more inputs. So that's really what this is showing us, is that the number of inputs that go in, it can slow things, it can really overwhelm the amount of compute power you need, or it could be efficient and move quickly. So to put this in perspective on why this is important. So I've showed you before that I've admitted this, that I don't write the most efficient code. So my code is not going to be winning any awards on any of the speed. But this is really, as you look at this chart, you realize that it's a matter of scale, right? So again, if you're trying to work at a company like Google or Facebook or something that has millions and millions and millions of inputs they're dealing with, they can't afford to have inefficient code, because they're going to quickly be up in this red area if they have any inefficient code. So it's very important to them, because they're further to the right on this chart. Whereas smaller projects, and when you're getting going, are way further to the left of this project or this chart. So you're not, the decision to optimize your algorithms is you should always be working towards that, but it's less important than getting the actual thing done. But I just want to show that this is something that exists, and one of the ways we could choose one algorithm over another. Is everybody tracking this so far? Do we have any questions about this yet?
Okay.
No? Okay. Cool.
So if you did this and had this in front of you,
Mhm.
And we were writing some code, right?
Yeah.
this would encourage you to go back and look at your algorithm again, maybe, if you were up here in the upper left.
Maybe there is a way to calculate your own algorithms, but I'm going to show you further why, this is great to know and kind of keep in mind, but we're not going to go into calculating for our own. And I'm not going to make you go through and figure out what your big O notation is for these algorithms that you're writing for the practice. But that is, if you look at LeetCode and you go to Code Wars and people post their answers and responses, you'll see that they'll put these little things at the bottom. They'll say, this was my solution. And they'll just say like O to the n complexity or something like that, or linear time complexity. So now you know what they're talking about. And so it won't be like, what does that mean? So there's less confusion when you're looking at those things, partly. But then also when we scroll down here, and I love it, you're like one step ahead of me on everything you ask, and that's great. So when we scroll down here on this page, we have a chart that shows data structures and certain operations that you would do with those data structures, and the time complexity that it takes, also color coded. So you can just look at this and try to say, okay, well, which data structure will I use and will it be faster? And we're going to talk a little bit about why these things work faster versus the others. I'm going to show a few examples using, we're obviously not going to go through all these data structures. It's way too much to get through. I mean, this could be a whole course just on its own, obviously. This is a lot. But the top three, we've already actually seen arrays. We call them lists in Python, but generally speaking, in computer terms, it's arrays. We've already seen hash tables. We call them dictionaries in Python, but they're really common, and it's a super fast way to do if you look at this box is search. But I guess to kind of take a quick step back and orient us on what this chart is showing. On the left-hand side, it has the list of the data structures I've shown a couple of times already. But in the center section is time complexity. So that's the amount of time that the CPU takes to process your algorithm or process an algorithm or do something with these data structures.
Point out where it says the time complexity.
Right up here.
Okay.
Right up there at the top, right? All right.
Yeah.
And then if you go all the way across over to the right-hand side over here where it says space complexity, this side over here, this is talking about the memory that's available. Remember, we've talked about memory and storage. Storage is stuff that's persistent and lasts for a long time, and memory is what's used by the program to store little bits and pieces within itself. Like when you set a variable, it's defining a space in memory. And we remember what that means is that space that's being defined is a set of ones and zeros broken up into 8 chunks called a byte, right? So it's arranged in bytes in a place in the computer, and that's called the memory space. And this is how complex these things are going to be when you do these operations. Then you also see this thing right here where it says average or worst. We talk about complexity in the terms of its best, average, and worst case scenario. And you usually want to look at the worst case scenario. And I'll talk about why that would be the case. But you usually talk about it in terms of the worst case scenario, because that's the one you want to have to deal with. And that's where things might break.
Best friend Murphy. He's always sending us there. Yeah.
Exactly. So that's data. We're going to go into data structures a little bit. I'm just going to skip down real quick to show that there's also specific section for algorithms. Now, this just has a list of sorting algorithms, or array sorting algorithms specifically. So far in this course, we've talked about algorithms as the general meaning of the word, and we've written our own. We've talked about what it is. You will frequently hear people refer to algorithms in this sense of ones that are well established and that everyone knows by name. Like Quicksort is an established algorithm for sorting arrays. It's one way of doing that. There are, as you can see, several ways of doing this. Is just sorting. This is just sorting arrays. And there are tons of ways of doing it. And you can see that they have all kinds of different implications on time complexity and space complexity. But this is just sorting. There's also searching is a major category of algorithms that are popular, and you should know a handful of them by name. Out of these, I think it's probably best to understand things like merge sort. We'll talk a little bit about how that works, and that uses recursion. So it's good to understand how recursion works. And bubble sort is another one that's pretty frequently talked about and used. We talk about how it works. Also uses recursion on how it does it. But that's really what this chart does. And so when we're making our decisions to do things, I'll show you a little bit about how you would do some things and why you would choose, say, like an array over a stack or a queue. Does this make sense so far on what we're looking at?
Yeah, I kind of get the gist of it.
Okay, cool. Any questions so far on what we've talked about up to now?
So if you were still coming back to the thing that you have this information in front of you, right, on a particular function or a particular piece of code.
Yep.
This would be a guide to go back and take action or something to.
Yeah, yeah. And when it's also kind of deciding what it is, what problem you're trying to solve. So let's go through some examples of I guess like arrays, stacks, and queues, and it'll become a little bit more clear. But yeah, that's a good question. Like why would you need this information? Like what decision are we making here? So let's make it a little bit more concrete with doing some messing around with stuff. All right. So I did a little factorial example. And let's talk about strings and lists. So we talked about these already as data types, as ones that we're going to use frequently. There are some things that if you joined us, or I think we were talking about a little earlier on, I'm not sure if we had the recording going for that part, but I think Chris and I were talking about, you look up the built-in methods, right? The built-in methods to a string, or the built-in methods to something that can do things for you. And we used split on the URL last time as an example of a built-in method for a string. So there's a lot of things that you could do with those that are built in, but there's also a cool way to manipulate strings. It's called slicing, that we can take parts off of it and just grab like the first part, the back part, or something like that. So let's do a quick example. I think I already have some example. Nope, I don't. All right, so let's just define. I'm down here in the bottom console here. I'm just going to define some quick examples, and I'm just going to say, you know, this is my example string. And so what I didn't cover before, strings are what's called immutable. You can't really change a string. So if you do things to a string, you're actually going to make a copy of it and create another spot in memory for that copy that you've done something to it. So what I did now when I declared this is I set aside some space in memory that exists and I label it X. And so it's full of a string. Now strings can do indexing like we did with lists. So I can get the first letter out of this string by doing just my string and then 0. And then it comes out just like we did the indexing before. And we can also do this thing called slicing, where you do X, the bracket. So the string that you want to use, the bracket, open square brackets. And then you can use this colon to be in between two indices, if you like. If you want to do like between the second and fifth indice, and it'll give you just the parts of the string that are between that. So I got is, the word is, and a space. So it doesn't include the fifth indice, but it gets the second one. You can leave it blank, and I'm showing this for a reason. We're going to go into the list for a second, and it's going to tie back to why you would choose a certain structure. So I'm showing some things we can do with them real quick, and then we're going to tie back to that efficiency piece. So if we leave it blank in the front, it assumes it's it's the very first part. So if we wanted to get all the way up to the fifth element, we would leave it blank. If we want to get after the fifth element, we would do just 5 colon and then blank, close the brackets, and it'll give us everything else in the string. So we could do similar things with arrays. And so if we do just like a quick example array that has a couple of things in it, doesn't even really matter what we put in here. Let's put in a few strings. So we can do the same thing. So we can, you know, index it like we did before, or we can say, give us everything that's, you know, up to our second index. I'll just do the first index, so there aren't that many things in there. So this is going to give us the first item. So up to the first index, not including the index number 1, which is B. So it doesn't include that one. So with a list, though, so with a list, and this is array, again, keep in mind arrays. That was the top data structure that we saw on our chart over here. So now when I say list in Python, I'm saying array generally. You can also use this slice to start changing the list and add things to it. So you can add something to the front of a list by using the slicing method. So let's say we got this 3-letter string, or we got these 3 different strings inside this Y array. So we got A, B, and C. Let's say we want to add a letter. So I'll do what I was doing before, and I'll do 0. So I do the bracket 0. So this means that like everything leading up to the 0 index, which basically is the 0 index. So it's everything before the 0 index. And then I'm just going to set it to whatever I want it to be. So this could be any data type. I'm going to keep using strings just for the example, but I'm going to throw this in there. And now when I look at this, it'll be inserted in the front. So there's the letter Z that I just inserted to the front. So that's one of the ways you can insert things into a list. And you can also add things to the end of a list by appending them to it. So I'm going to add another letter by typing dot append, and this is a method. So it's a built-in method to lists. All lists can append like this. And then we just put in what we want to append. So if I want to put the letter W in here at the end, then I do. I hit append, add W. Now it's added to the end. So that's how you add things to the front and the back. Cool. We can also take something off the back by using the pop method, and that's built into it. So we do y.pop, and that'll print out, it'll return what was removed. And just to prove that it's not there, we'll print out y and see that the W isn't there anymore. So you can capture that into a variable or something like that if you want to.
So I'm guessing push is the other function to add.
Nope.
So if you,
Nope, that's append. That's so push
Okay.
would be for, like, I think push is the syntax for JavaScript. So don't confuse it. That is the way to add for some things, but append for Python. If you're
now
adding,
can
and
you
that- and that'll
also
append at the
take
end.
Y and just use plus? And W
Um,
and include the, will it do, is it smart enough to
well, let's find out.
take that there?
Let's see. Nope.
Hmm.
Can only concatenate list, not string to list. So we can do y plus the list that contains, say, another letter. And so then it has X at the end, but it didn't save it. So you see it concatenated it, but I didn't store it anywhere. So yes, you can concatenate lists by adding just the plus sign between two lists and put them together.
Okay.
But it doesn't persist unless you save it somewhere else. So it doesn't change the actual list itself.
But that's valuable too, because
Yeah.
sometimes you don't want to do that. You want
Yeah.
to
Just stick them together. and
assign
put them in
that
the same
to a new
place.
variable. You don't want to create a new or modify your original data. You just want to make a new variable that contains the two lists.
Exactly. And that's a concept. I'm
Yeah.
glad you brought that up because that is something that we want to keep in mind here. Because I'm going to loop this back to efficiency. I promise. This isn't just a talk about lists and all the things they can do. So with these basic functions, well, and there's another one we can do here that I want to talk about real fast, another method called insert. So you could put something in the middle of this if you wanted to. So you could do, if I can remember the syntax for it, it's insert. Believe we do index and then element. So if I want to put something in, we've got 4 elements in here. So if I do the second index and I want to put that W back in there. Hopefully this doesn't break. All right, cool. All right, so now we see that the 2 index was the letter B, and then I ran the insert function or method on this list, and I inserted W into that place. So it just moved everything around and put it in there, but it's in that same spot. It didn't make a new one. So that's really good. Yeah, good to point out, Chris, that when we concatenate together, it doesn't automatically make a new one. It doesn't change. It automatically makes a new one. I'm sorry. It does not change in place the array that we already have or the list that we already have, even though that's possible because lists are changeable. So, all right. So those are the last things I want to show real quickly, how to slice. So slicing is a way that you can, take parts off of a list, or you can add things to it by adding something to the front. You can add to the back by appending. You can move from the back by popping, and you can put things in the middle by inserting. Now, when you look at this chart, and we go back to this chart, and arrays are not the fastest with insertion and deletion are the things that we talked about. It's not terrible, but it's in the yellow, right? And it's these stacks and queues are faster ways of doing that. The reason that would be is that when we change a list, first when we make a list and it sets aside that area in memory, that's a fixed size in memory. So that's one spot that the computer is designated as this is how big it's going to be. So anything that changes the size of that makes the computer do extra work to take all of the array out of there and move the whole thing to another place. So it makes some operations like the ones we just did slow. And there are faster ways to do certain things. I'm going to use some non-code, but I want to write out some examples of like these next 2 things that we're doing here. The next 2 data types that are sometimes faster than arrays, but you can use lists to think about them. So they're called stacks and queues. So then they're the next 2 on this list of things here underneath array. So, and you can see that here they're faster for insertion and deletion. So I'm going to talk about why that is. I'm going to try to show why that is a little bit here. And it shouldn't be too complicated because these are not very complicated. But I really just wanted to use this to demonstrate the choices that you make when you're choosing a data type, right? So we think about lists again, they're written in one place. And every time you change the size of that list by doing the chopping and slicing and things that we've done up to now, you're moving it around in memory, and it's a little bit of a costly operation. So the other options for this particular sort of thing, which is called stacks and queues. We'll start with a queue because it's probably easier to picture, I guess, for the beginning, because it's a lateral thing anyway. So a queue, if you think about a queue, that's what, if you're in England, that's what we call a line. You line up for something. That's what it would be. They call it queuing up for things. And so if you imagine like, say there's well, hold on. We can just start with a list. So a list is a way that we could think of a queue. Again, it's similar to a list. So we're represented with a list. Let's imagine we have this list and there's, say, one person. And again, if you don't know what this is, I'm leading with hashtags. So I'm commenting this code out. So it's not going to run. So I'm not writing Python code. I'm just writing notes so that we can see what I'm talking about to extend the idea of this queue. So say we have several people standing in a line and they're waiting to go up here at the front of the line. Let's say, I don't know, it's a movie theater, right? So who cares? Movie theater, and it's closed with double doors. And when it opens, the first person in line is going to move forward and go this way and go into it. So in terms of our list, the first person in our list is going to leave and go in. And as other people come in, they're going to line up in the back. So other people can come in and they're going to add to the back. So this is a queue. It's called enqueuing from the front, and so add from the back. You add items to the back, and you dequeue in the front. So what we talked about before with lists, as you see, this is a list, and you can think of a queue as a list in Python. You can actually make a queue in a list, but it is very slow compared to an actual data structure of a queue, which you would do a slightly different way to make it. You use a built-in library in Python. It's called Deque, even though it's spelled DEQE. You would import it and use it that way. So we're not going to go through the full implementation of it because it's very similar to lists. It looks a lot like lists, but it's handled differently in the memory. So the key important part here is not the code and how it works. So the code is going to be written very similarly to the way you would with a list. It's understanding that the list itself is an inefficient way to do this, even though it is something you can do. So just like when we did this example with recursion, you may not always want to use recursion. You may just want to use while loops. There's other ways to do these things. But just know that if you're doing something like a queue, so if you're doing a practical application of this, of first in, this is called first in, first out, FIFO. If you're doing something like this, like a customer service queue or any of those sorts of things where it matters who got in line first, then you can use the things that I just mentioned with slicing out the zero and, the zero index of a list and then appending to the back. But that's going to be slower than if you use the data structure that is a queue. So as we can see here, insertion and deletion, when we go back to this chart, is faster with a queue because it's constant time. Even in the worst case scenario, it's still O to the 1, which is, if we go back to our chart, that's really what we're shooting for down here, as opposed to an array for any insertion and deletion, which is what those people getting into the queue and people going into the theater, going into the theater is deletion, getting into the queue is insertion. Arrays are O to the N, which is slower. So but when you're looking at these and if you're saying, okay, my performance and speed is really important, I don't want it to be slow, then you would choose one or the other. But if your space complexity for your memory is important, they're the same and it doesn't matter. So that is one example of how you would use this information on picking what you would do based on the problem you have at hand, right? So let's say, again, you're trying to make an application that has people coming into it for customer service and they're trying to come to you for that. And they logged in and asked for customer service at a particular time. So they have a timestamp associated with them. And you want to drop them into a queue for customer service reps to deal with and grab the first person in line and deal with them and add people as they go. That would be a queue. And it's faster than doing this with a list because it's in memory, something that's not restricted in size. So when you use the queue itself, which again we would import this package called, this is pronounced DEQ, even though it's spelled DEQE, stands for double-ended queue. And it has ways of adding things to the back and removing things from the front, and flexible space that a list doesn't have. And so your list is going to be slower, more and less efficient at doing something like a queue, even though you can do it with a list. So does that make sense? Have I lost anybody yet?
No, I think I see what you're getting at.
Okay. Have I lost everybody? No. any question? I'm gonna kind of pause there for a second, because I know that's quite a lot. And honestly, these data structures are a little more complicated, and it is a little more ethereal. And like, when would we use this? So I'm trying to make sure that we're grasping some semblance of a practical application for why you would even do one versus another.
Yeah, because you can get multiple structures that'll do roughly the same thing, right?
Exactly. And that's going back to, if you remember, when you made the peanut butter jelly sandwich, which was delicious, by the way, because my kids didn't eat it, so I ended up eating it. But
Right.
and we talked about it afterwards, everybody else had some inputs on, like, you could have done this, you could have done that, and those were all valid answers. And just like the algorithms, when you do the practice and see other people's answers that I demonstrated on Tuesday, you'll see that other people come up with them, and even the ones that are voted up as really good, there are a lot of really good ways to do it. So yeah, it's that there's a myriad of possible solutions.
Yeah.
And
But
even though, go ahead.
if I did it again, right, the whole
Yeah.
peanut butter sandwich thing, yeah, I would think there were some tweaks I could make, some changes, right?
Right. And so that's going at it again. So if you're in a position where you're looking to become a developer and go through coding interviews and things like that, they'll have you solve an algorithmic problem like the ones that I put in that set. And it could even be one of those that's in there. You know, they if you on LeetCode, it shows you which companies ask those problems. And so you can focus in on a specific company. If you're really looking to work at Google or something like that, you could do ones that they ask at their coding interviews. But typically what they'll do is they'll ask you to solve it. And then if you come up with a viable solution, but it's not the most, efficient solution, or even if it is, they may just ask you, that's good, but can you do better? And so this is really what you need to know here to be able to answer if you can or cannot do better. Because sometimes you can't, right? Sometimes that is the best you can do. But this is where you would know. And this is an algebraic way of actually measuring, empirically on what way to do something is faster for a particular function that you're doing.
Okay.
So any questions, any confusion on that, on array versus a queue? And I'm not going to go through, again, implementing the full DEQ thing. It's in collections, the way you would import it if you're curious. I mean, you should look it up. It's something you should look up if you're curious about these things further. This is a little deeper than we're going to do, but it's from collections. You import DEQ, and then you can do all kinds of cool stuff with it, and it's not as slow as a list. But we're not going to step through all that. Another thing, though, I want to show as an example is the stack, which is it's very similar to this. That it's like a queue, and it's like a list. It can be implemented with a list. It's better to be done with DEQ, like I just mentioned. But a stack is, if you think about, say, like a stack of I'll do another list. Let's do a stack of plates. So this is a plate, like a dinner plate you eat food off of, right? And so there's a bunch of plates. They're all the same, no difference. And imagine being stacked up, like in a rack or something like that. And on this side of the rack, you got a dishwasher. This is at a restaurant. So there's a dishwasher, if I could spell, that's putting things in here, putting dishes in there. But then you also have, so it's adding to the end. Then you also have in here, so like a line cook taking stuff off. So he'll take the last few dishes off the end. So this is going to add to the end, and it's going to take stuff off the end. So it doesn't matter at what point something was, it doesn't matter if the first one was dealt with first. It can just, the last one can just, or the first one can just sit here. And this can be, arbitrarily deep. It doesn't matter how many plates are here. It's always going to come from the back. So,
like an ammo clip for our guns, right? This is all military.
Yeah, exactly.
The first bullet you put in is the last one that cycles through the gun.
Exactly. And so
That's
this
just
is
you're
this,
loading your clip. So the last bullet in is the first one out.
right. So this is called last in,
First out,
first,
LIFO.
first out, right? Yep. So LIFO. And again, this could be implemented. You could do this as is written here with just a list, and you can just use pop to grab the last one. So the line cook can be doing pop to pull stuff out, and you could be doing append. The dishwasher could be doing append to add stuff. But it is going to be slower if we look back at this to do exactly that thing. To do those same operations, it's just going to be slower to do with a list than it would be to do with an actual stack. And so the example of when you would want to use these, so like the queue, again, if you're doing a customer service queue, that's when you'd want to use a queue. In a application example, this sort of thing can be used for if you want to write in like an undo function, so it can reverse a string in an array really well and put, if you have a string, like if somebody's typing into it, it'll reverse the string that they typed in, and it can give those, those keystrokes back as an undo thing that you want to build an undo into a, I don't know, text editor or something like that if you're making one of those. So those are some examples of how the choice of data structure can affect the speed of your overall program based on how many inputs you're going to put in. So again, even the decision between those two, you have to get to a lot of inputs before it's really a big difference, right? So if you're down on small on the left end of this chart, the choice between those, if you saw, was between O to the N and O to the 1 for stacks, queues, and arrays. And you're really just deciding between these things, between not so good and really good. Cool. Any questions about that?
Nope.
No? All pretty straightforward.
No.
Cool. So the other bit that I want to talk about today, along with algorithms, and we've talked a little bit so far about them. So we're just going to go, I guess, into some examples of sorting algorithms. Maybe they have down here, sort of how these work and recursively. And I really encourage everybody to go to this thing and look at it. And what's cool about all of these is they have a link to the Wikipedia page, which has a full explanation. But if you look over here on the right hand side, and let's see if I can blow this up, zoom in a little bit, it has an actual animation of how this works. So this is showing how a merge sort works, and what it's doing is the program will recursively go through this unordered array, and it'll break it down into individual things, and it'll compare the elements of that and start ordering those into smaller ones. And so what we're seeing is a recursive function that's looping back through and doing each of these steps over and over again until it reaches the condition of this being in order. So this is one way to sort an array. It has, its own implications on how fast it is, how you can, how you want to do it. But this is one way to approach it. Another big set of algorithms outside of search or sort algorithms is search algorithms. It's one of those things that you're definitely going to want to be familiar with what they are, what the popular ones are. So, again, I really encourage you to look at, well, now it's all gigantic, to look at this cheat sheet page and the algorithms that are listed here. But out of those that are listed here, things like quick sort, merge sort, and bubble sort are also really good to understand that what they are, what they do, if there are any complexity differences between them when you might choose one over the other. So those are ones I would definitely highlight. And bubble sort's cool because it kind of just takes two, looks at them individually, looks at them in pairs, and then goes all the way back through and iterates through again. So this is just an example of how many different ways there are to do something as simple as sorting an array and putting them in order. Then the search set of search algorithms, they kind of go through, they're grouped by their mechanism of search. And there's three main mechanisms for searching. So you have linear search, binary search, and hashing are kind of the three main ones. And we're not really going to implement them, but I'm going to use some, some kind of pseudocode here maybe to help picture what those things are. Linear search, we've already sort of done. So linear search is going through and looking at each element within something and seeing if it is the element you're looking for. So if, say, even if we use this array up here in the example for the queue, and we'll just say this thing, and we're looking for person number 3, we're going to have to search through all of these and say, okay, is this person 3? No. Is that person 3? No. Is this person 3? Oh, it is. Cool. We found it. And so it's either going to find the thing or it's going to go all the way to the end of the array before it ends. So linear search, that's called, is one of the least efficient ways to search. And this goes back to why we talk about things on this big O chart in terms of the, best, average, and worst case scenario. We're generally talking about the worst case scenario, because in linear search, you imagine if the item that you're looking for out of, say, like you've got 1 million things in your list, if the item you're looking for is the second one there, that'll be pretty fast. It'll find it really quickly. But if it's the millionth thing there, or if it's not in the list, you're going to have to go through all of those things, and that's your worst case scenario. So it's not a fast way to search for things. Now, an example of a very fast way to search for things is called binary search. Again, we're not going to go into implementing this exactly, but binary search takes an array and it'll find the midpoint. So it has to be a sorted array already. We talked already about things that are sorted. So once you've made that choice to sort something, you got to figure out how you're going to sort it for its speed. But then if you want to search in it, it's got to be sorted already to use binary search. A good analogy for this to understand how this works is like a dictionary, not a Python dictionary, but a language dictionary that has lists of words in there. I don't know, the last time I was thinking about this when I was putting this class together, I don't think I've actually used a physical dictionary in like 15 years. Now I just look things up on Google for the word definition, right? But we do remember the ancient technology of a dictionary that has things listed alphabetically, and binary search is a good way to think of that. So let's say we're looking for a word in this dictionary. It's going to be separated A to Z. What binary search is going to do is it's going to split that in half. The first thing it does is it splits it in half. And then it takes the midpoint. So let's say we're looking for a word in the dictionary that starts, let's say we're looking for book in the dictionary. It starts with B. So it's going to take the midpoint of the alphabet, which is the letter M, right? And it's going to say, okay, cool. So that's letter M. Does the search term that we're looking for, is it in the group? It's going to split on M and make 2 other sub arrays and say, okay, is book that we're looking for in the first array or is it in the second array? And that general, like, does this thing exist in my collection? We've seen that already in Python. Is like, is this in the thing we're looking for? Real common in computer science. So it's going to say, is book in the first array or the second array that we split on M? If it's in the first array, then it'll do that splitting function. It'll recursively go back. It'll take that first array as its input. It'll split it again and keep doing that splitting in half until it finds the thing that it needs. And this is a lot faster than linear search. So binary search is faster because it cuts the thing in half each time. So it goes faster and faster and faster. So that's the second big way to do it, but it's got to be a sorted list that you have, a sorted array that it has. So there's linear search and binary search. I guess I didn't label linear search on here. Even though I'm not showing examples, because again, we're not going to implement these things. It'll take a little while to write out full code to do that. But I want you to be aware of these things and the choices you can make with them. Especially when you're going through the things that you're doing here. And the last one is hashing and searching. So using hash tables, as you might hear them called, or hashing is the fastest way. There's the fastest way to look something up out of a collection. And that's using basically a key value pair, so a dictionary. So if you can put your data into a dictionary, it's a lot faster to say, like we do now when we're looking for a word and type it into Google, and I just type the word and it gives me the definition because it found that word by the key in a big like Python dictionary of things, and it just has to go straight to that key, grab the key, and come back with the definition. That's it. So that's by far the fastest way to search for things. So if you get into a hash table and you can hash the things you have, if search is what you're doing, that's the data structure you want to use. That's the algorithm, because it's going to use that algorithm to search.
So going back to the dictionary analogy, right?
Yeah.
So you want to look up the word tree, it would take you right to tree, and then you retrieve the definition, right?
Yep. So if you're using hashing for your search, then you can go straight to that key and pull it right out, and you don't have to look at anything else in that collection at all, and just grab it and roll with it. It's by far one of the fastest things you can do.
Okay.
Great. So I left some time to talk about the algorithm things that there's hopefully people have done. So if you wanted to go through one now, if you wanted to break here, you can and go dig into something. I know we went through some fairly more complex things this time than we have in the past. I don't expect everyone to like start using binary search and recursion to solve everything. This is more to be aware of somewhat the next steps. If you're already blasting through the algorithmic challenges that I gave already, then start studying these things, because this is the next step. This is really where you start doing the efficiency and picking the things that you're going to need for larger scale projects or getting ready for coding interviews and that kind of thing. So any questions about any of the things that we covered today or that we covered at all in the course up to now?
Not for me.
No? Okay, great. So then next week, what we're going to do is, and again, I really encourage everyone to take these next few days and between now and Tuesday and practice these things. Go do the algorithmic stuff, work through it, read some of these articles on some of these things. Next week when we come in, what we're going to do is we're going to start building the actual web application that we've kind of talked about a few times. So I'm going to show you what it looks like so you have a sense of what it is we're going to build. And then I'm going to destroy all this over the weekend and we're going to build it together from scratch. But I want to show you what it looks like so we have an idea of what it is. So when we get in here, this is something, if you really feel like doing it, you can play around with this on your own. But you flip over to the web tab in Python Anywhere. And if those of you, I guess actually this is another point. If those of you who have not been doing it in Python Anywhere up to now, that's fine. I said you can do everything locally and you totally can. But this here is going to also be our deployment step, right? So we're going to build and deploy the app right here. So if you're running code and writing the code, you can do all the things that we're going to do next couple of weeks in Django. You can do all that stuff on your local machine, but then you're going to have to go the other step of moving it into something that deploys and being able to see it. Whereas if you do it here and follow along with us here, on Tuesday, we're going to have the backend set up and you'll be able to, it'll just be on the internet. Like you'll have your own app at your own site. And it's going to follow this convention of, you see, it's my username.pythonanywhere.com. That's going to be yours too. So your website is going to be that when you make the app. And it's going to be in this web tab. So I'm going to go through like how to set this up and all the settings. So don't sweat it now. I just want to give you a taste of kind of what we're going to do. But this is going to be the URL that you're going to go, and you're going to have your own. It's going to have your username on it. I see this. Sometimes this gives me some issues when I try to run it the first time. Let's try it again. There we go. All right, cool. All right, so this is a real simple 2-page website that we're going to build. I'm going to show you how to grab assets from online and drop them into a basic HTML page on this page, a couple of navigation items at the top, and then we're going to go over to another page that has a to-do list on it. And this is a very basic, simple to-do list that you can look at the list items that are here on this in the middle. You can edit them. You can add tasks to it, right? So you can say new task, give it a due date, give myself some time for this, and say it's to do, and hit submit, and it'll add it right there to the new task. And say, oh, you know what, that's not good enough. I want to edit this, and say, get your life together. I might need some more time for that. Give myself another year, and hit submit. And now it's updated. So there's, my new task. And then we can also delete the task. So I can hit delete. You see this little JavaScript warning that pops up. It says, hey, do you really want to delete this task? And we'll say, yeah, I do, because I'm not worried about getting my life together. So we're going to delete that task. So that's what we're going to build. We're going to build this from scratch. It's going to look roughly like this. Again, it's not a front end course that we're doing. This is more about functionality and back end. And the reason we do a task list, the reason we do a to-do list is every application that you operate, use, interact with on a daily basis can be thought of in a task list, right? So if you use, I don't know, Instagram, whatever, the tasks are pictures that you put up there and they're comments that you put in. You can see them, you can edit them, you can delete them. And this does all those operations in a very simple way. So the database that we're going to make isn't very complicated. It doesn't have a lot to go into it, but it's going to give us a hands-on experience with all the mechanics that you would need to build really any application anywhere, not just a web application, but any application. It's the same general patterns that we're going to follow within the framework of Django is the name of the framework we're using. So it's written in Python. It'll enable us to do this. And that will be next week. So with that, we can wrap it up now if there are no other questions or anything else.
Yeah, I'm gonna spend my time trying to catch up to where I should be.
Excellent, excellent.
Yeah, same here.
Me
Okay.
too.
Because it's going a bit fast. I have to go through the recording.
Mhm.
And just stop and look carefully and make sure I can do it on my own.
Yeah, yeah, for sure. Absolutely.
Me too.
Okay.
Yeah.
Yeah, excellent. And that's, and it is, hopefully it's not too fast and you're feeling lost. If you are, let me know. I can slow things down a little bit and we can tend to spend more time on things before we just keep adding more stuff to it. That was somewhat of what today is too, is that it was kind of a break from actually doing and writing things and more just kind of concepts and how to apply them, maybe, places to stretch and get better.
No, it's not that I'm lost. It's just that
Yeah.
I'm behind. You know what I mean?
Yeah, good. And that's what I'm saying. That's what I'm hoping. I'm hoping that's where you are. Because again, I'm trying to make this like real boot camp where you got, when you got there and you first started running, even if you were in decent shape, man, it was fast. It was hard to keep up with. And, I don't want you falling out entirely and getting in the truck and not running anymore. But I do want it to be a struggle. I want it to be difficult to a certain extent. So I'm
I'd say
hoping
you
we'll hit that
succeeded-
sweet spot. But
You succeeded so far.
okay, good. Good. But I do want to keep throwing out there. If somebody's feeling lost and really struggling, I'd reach out, let us know, because there's no need to fall behind and give up. This is something that can be self-paced and you should be able to take it at your own speed. If you can't do it in 6 weeks, that's
The
fine.
biggest problem I've had so far with this whole thing, on Windows 11, you could get a split screen on your computer, so you can look at two screens at once.
Mhm.
I had forever to get that to work.
Oh, yeah. That's frustrating. Diane, you have a question?
Yes. Can you hear me first of all?
Yes. Can.
Okay.
Welcome.
I had hell getting to you.
Oh.
Okay.
Oh, sorry. I said all that and then you froze.
I'm gonna jump off, Jeff. Thank you
All right,
so
Marnie.
much.
Yeah, thanks a lot. Absolutely.
right.
Reach out if you got questions. Have a good one.
Okay, thanks.
I'll see you next week. You're gonna put this you're gonna send this, right? This
Yep.
recording?
I'll email it out and I'll put it in Discord like I have with the rest of them.
Okay, all right, thank you.
Right. Yep. Have a good weekend. See you Tuesday.
Yep.
not here for
No, I think Diane's still messed up over there.
me.
That America Online dial-up.
Yep. Taking me back to the olden days of the internet.
God. Can't tell you how many support cases I had for the sales guys that would install AOL on their work laptops and break everything.
Oh, nice.
All because they didn't know how to get their email without AOL. It's like, well, because we pay millions of dollars a year to have corporate resources.
Yeah.
Yeah.
That's terrible.
Nah, really, it's about control. They wanted to know if they ran to the next company, they could take all their customers with them.
Oh, yeah,
They
absolutely.
they didn't want them.
Jeff,
So
you
they played dumb, but
What's that, Brandon?
you're still recording? I don't know if you want to be.
Oh, yeah, I can stop recording now since we're done with this section. Yeah, thanks, man. I forgot I haven't stopped recording yet.